Welcome everybody to today's webinar. My name's Daryl McKenzie. Our webinar series is something we've been starting to initiate over the last few months, just as a way to sort of share the love and spread some knowledge about different things we can do in statistical ecology. And today's speaker, we have Stefan Mayer, who's going to be talking about tag loss in mark recapture models. So during the webinar, if you have any questions, please pop them into the chat and we'll try to respond to them at the end of the session. So with that, I would like to pass it over to Stefan.
Well, thank you, Daryl. I will just start sharing my presentation. Just double checking with you, Daryl. You can see it on your end, I suppose.
Yes, all good.
Cool. Okay, Daryl, thanks for the little introduction. So as Daryl said, today I'm talking about tag loss in mark recapture modeling. Just try to move to the next slide. Here we go. Yeah. So just before I go into the topic, just wee words about myself. So again, my name is Stefan Mayer. I'm an ecologist by training, and I'm working as a quantitative ecologist at Proteus for like 4 or 5 years now. And I've been mainly using Bayesian modeling in a fisheries or population modeling context. So this is the main work that I'm doing. And as I said, today I talk about tag loss in mark recapture modeling. In this presentation, I will start explaining what are the reasons for tag loss and what are the implications. Then for those, I mean, I assume that most people are familiar with mark recapture modeling, but for better understanding, I give a very brief recap of the Cormack-Joly-Sieber, or in short, CGIS model, and how this can be implemented in a Bayesian context. And then I provide or demonstrate a very basic tag loss model, so it's clear to everyone how it works. I explain how I derived it, and then how this can be implemented, in this case in JAX, which is my Bayesian language of preference, basically. And yeah, I basically provide a very technical instruction how this can be done, and then I finish off with a simulation to show everyone how this model performs, and again to demonstrate the implications of tag loss. So when I'm talking about tag loss, I have to make clear that I'm only talking about temporary marks, such as tags on pinnipeds or rings on birds or all kinds of other temporary markings. So here in this presentation, I'm not dealing with any permanent markings, such as, for example, dorsal fins in dolphins, for example, or scars on some animals. So there are obviously many reasons why tags can get lost, and I can just list a few. For example, corrosion can be a big impact or have a big impact on metal tags, as you can see in this figure down here. Therefore, tags can simply fall off. There can be infections at the tag site, and this tag is simply discarded off the skin or the tissue. Usual wear and tear can occur through UV radiation or salt water, or the habitat such as rocks if animals rub their body against like some structures such as rocks. Incorrect application can also lead to tag loss and skin growth. This can have serious implications for the estimation of our model parameters, such as survival. So yeah, implications can be, for example, the loss of precision, the underestimation of survival, and also the underestimation of the population size, depending on what type of model we're implementing. In this presentation here, I'm only talking about the impact on the estimation of survival rates. And before I jump into the topic, here just a list which you can look up further. Here I will provide a PDF version of this presentation later on, so you can have a look. Just a list of, I found very useful papers that explain how tag loss is impacting estimates in mark-recapture models and how this can be managed. And I just highlighted 2 papers that are basically the baseline of what I'm presenting here today. So I said I give a quick reintroduction or recap into the CJS model. And I keep it very simple. I guess everyone is mostly familiar with it, but it's just good for a context. So assume we have tagged an animal or several individuals at an initial occasion, and then we have 2 subsequent recapture occasions or years, for example. So in order to see an individual in the subsequent occasion, the individual has to survive with some survival probability phi until the second occasion, and being seen at the second occasion with probability p. And then in order to see the animal at the last occasion, the animal has to survive from the second to the third occasion with survival probability phi 2 and be recaptured with recapture probability p3. So if we have 3 occasions, with the first occasion being the release occasion, then there can be 4 different encounter histories. The first being all animals the animal being seen at all 3 occasions. The second being an animal not being seen at the last occasion. The second last being the animal not being seen at the second occasion. And finally, the animal not being seen at the last 2 occasions. And for each encounter history, there exists a probability. And just give you a couple of examples. The first encounter history, the probability would be the product of all the 4 different probabilities, of phi 1, p2 times phi 2, and p3. And then for the second encounter history, the probability is the probability of the animal surviving from the first to the second occasion, phi 1, times p2, so the recapture probability at the second occasion. But then for the last occasion, the probability statement is either the animal hasn't survived with probability 1 minus phi 2, or the animal has survived with survival probability phi 2 times the animal has not been seen at the third occasion, so 1 minus p3. And then we can count the number of individuals in each encounter history and use multinomial likelihood distribution to estimate the different parameters. So I think we're all familiar with that. Another approach to estimate survival and recapture would be to implement a state space model that can be either done in a likelihood context or using a Bayesian modeling approach, which is my personal preference here. And a state space model is basically splitting the process up in 2 separate processes. The first would be the observation process, so what we actually observe in field, and then a state process with a latent state, so which would describe whether the animal is either alive or dead. So starting at the top here, I would like you to focus first on the left-hand side table, just to make clear how the data would be coded and what the different label refer to. So for our observed states, animals or the observations would be labeled as 1 and 0, which refer to the animal either being seen or not seen. Then we can model this observation process as y, which is our observation of individual I at occasion t, given the latent state of the same individual at the same occasion. And this can be assumed to be drawn from a Bernoulli distribution, which is parameterized using the product of the latent state z at the same time times the recapture probability. And this can lead to an observation history of, for example, 1, 1, 0. So the animal has been seen twice and not seen at the last occasion. And again, the condition is that the animal has always been seen at the first occasion, which is our release occasion. And then we can model our latent state or state process. And again, this can be labeled as 1 and 0, which means that the animal is either alive or dead. And here the state process is again a Bernoulli draw, but we start first with the first occasion. Again, here the assumption is, or condition is, that the animal is always alive at the release occasion. And then the subsequent occasions or latent states can be modeled as Z at the next occasion, so T plus 1, given Z at the current occasion, being drawn from the Bernoulli distribution of our current, which is parameterized with the product of the Z, the current latent state, times the survival probability. And the potential underlying latent histories are either 1, 1, 0, so alive, live, and dead, or being alive throughout the entire study. So this would be the CJS model that can be used for estimating survival and implemented in a state space modeling framework. And now I want to use this to develop a model to estimate tech loss. In this case, or in this presentation here, only dealing with independent tech loss and for double-tagged animals. And I'm going to define this a bit more clearly in the upcoming slides. So just to give you a bit of an idea where this is applicable, there is one example that I used to work with in the past, and these are New Zealand sea lions. And New Zealand sea lions were known to lose their tags, and for several reasons. For example, in pups, sometimes the wound would fail to heal, and that can lead to result in tags being lost in young animals. Then also male New Zealand sea lions are significantly larger than female sea lions, and also their flippers are thicker. And due to that difference, and this the thickness of that flipper is thicker than the tag shaft, and that can lead to higher tag loss rates in male New Zealand sea lions as they grow. And then simply in older animals, or as they age, there occurs simple wear and tear, again, simply caused by, for example, salt water, UV radiation, and rocks as animals enter and leave the sea. And therefore, animals have been double-tagged. And this provides opportunity to develop a CJS model that accounts for potential tag loss. So how can we develop such a model in that context? Again, we can use the same approach that I just explained before, but now we have to expand the survival or alive or dead model into a categorical model where we account for the different tag states. Again, I'll just guide you through the different states first. So again, at the top left-hand side, we see the different observed states, which I labeled as 1, 2, and 3. This is by preference. So state 1 refers to an animal that is alive and retaining 2 tags. State 2 is an animal that is alive and so retaining 1 tag. And then the observed state labeled as 3 is an animal that has not been seen, because animals that have 0 tags retaining are unobservable. And the observation process is again Y given the latent state Z, and this time assumed to be categorical distributed. And the categorical distribution here is parameterized using a matrix, in this case theta, and theta contains all the different recapture probabilities for each of the 3 different states. And I'm going to explain the exact parameterization of that matrix further down the presentation. And one potential, this is just one example again, observation history could be 1, 1, 3. That means the animal has been seen with 2 alive and with 2 tags in the first and the second occasion, but then hasn't been seen in the third occasion. And then the state process has potential for different latent states. The first being an animal that is alive and retaining 2 tags. The second, the animal being alive and retaining 1 tag. And then the third state, the animal being alive and retaining 0 tags. And then we have the fourth state, which is an animal that has died. The state process is again made of two different processes, or no, one process, but we have to account for the latent state at release. And in this case, the condition again is that the animal is alive and is wearing two tags, because this is simply the state where we apply the tags to the animal. And then for every subsequent occasion, again, we have the latent state in the next occasion given the current latent state being drawn from the categorical distribution. Again, in this case, parameterized via another matrix labeled as omega, which contains the different transition probabilities between all the four different states. And based on the example above here, where we observed in history of 113, so alive two tags, and not seen, the potential underlying latent history could be an animal that has been seen with two tags at first and second location, but then either been retaining two tags, one tag, or no tags, or being dead. And again, just a reminder, only the first two latent states are observable. Okay. So how can this be? So now I'm explaining how I can derive the different transition probabilities between all the different tag states. So what you see here is basically the life cycle of tags. So we see here three different states. So an animal that is starting off with two retained tags labeled as tag A and tag B. Then from one occasion to the next, for example, from one year to the next, only one tag might be retained, and then only 0 tags are retained, or both tags are lost simultaneously. And obviously, the animals can also retain tags from one occasion, both tags from one occasion to another, and also the single retaining tag can be retained from one occasion to another. Before I derive the different transition probabilities, I need to define a few things. So first of all, our tag loss probabilities. So in theory, we can have separate tag loss probabilities for each flipper. So we have probability, I labeled it here as Q. So Q underscore A, which is the probability of tag A is lost. QB is the probability of tag B is lost. And then we have two conditional probabilities. One is the probability of tag B is lost, given that tag A is also lost. And the probability of tag B is lost, given that tag A is retained. However, since we have no permanent markings sorry if there's any noise in the background, there seems to be some fire alert testing. So at least it's distracting for me. So since we have no permanent markings, which I explain later on a little bit, it will be incredibly difficult to estimate separate tag loss probabilities for each of the two tags. So therefore, we assume independent tag loss. And I explain this now what this means. So we assume first that the same type of tags is or have been applied on both sides, so on both flippers in the case of the C-line example, and that tags are lost independent of which flipper it has been attached to. So that means the probabilities QA and QB are the same, so we just have one single tag loss probability, Q. And then also tag loss is independent of the loss of the other tag. So the conditional probabilities that I just explained are actually equal as well. So we can simply assume overall that there's one single tag loss probability. Or this is the assumption for this model here. Then we also assume that tag loss is time independent. So we can introduce some age structure, which I don't do in this example here, but we assume at least that throughout between two occasions, tag loss is the same, and that tag loss also doesn't vary between individuals. So going back to the life cycle graph of a tag or two tags, we can now derive the following probabilities. So I'm starting off with simultaneous tag loss, so losing both tags from one occasion to another. And that simply means that tags A and B are lost. So we have our what was original QA and QB, only now being Q, we just multiply them, so the probability is Q square. And then the next transition in this graph could be the loss of only using one tag, so either tag A or tag B. So that means this probability is made of tag A being retained and tag B is lost, or alternatively, tag B is retained and tag A is lost. So 1 minus Q times Q, or so plus Q times 1 minus Q. If both tags are retained from one occasion to another, that means that tag A and tag B are not lost, which is 1 minus Q times 1 minus Q. Finally, or second last in this example here, an individual which has one tag retaining can also lose that single tag, so making this transition here. And this is simply the probability Q. And this could either be tag A is lost, or if tag B was retained, this is tag B being lost. And then finally, we have an individual which is retaining its single tag or last tag from one occasion to another, and this is simply probability 1 minus Q. And individuals that have lost both of their tags, we're assuming that individuals are not retagged, simply remain within this stage here. Hence, the probability of staying in the stage here is 1. And this is just, again, all probabilities here listed, which we now have to, however, we have to expand this here because this is just the life cycle of tags. If we need to introduce a fourth state, if we want to introduce survival, and this would be a dead state, which I explain now. So we need to first multiply all the different probabilities by our survival probability, phi. And in this example here, I simply assume that there is no H structure. Of course, we can expand this graph by adding in some other structures, such as H or location. And we can also assume that there are different tag loss probabilities for different H stages and so on. But I keep it simple here, so it's understandable. So we now need to convert this life cycle graph into a matrix for our state process. And this is a 4x4 matrix with the state at the current occasion across rows and the state at the next occasion, t+1 across columns. And again, the states are 2 tags and alive, 1 tag and alive, 0 tags and alive, and dead. And so then we simply plug in the different probability statements into a matrix, depending on our departure and arrival state. And then we also need a matrix for the observation process. And this is a 4x3 matrix with the true state or the latent state across rows. Again, the same states that are introduced before, 2 tags and alive, 1 tag and alive, 0 tags and alive, and dead. And then the observation at the same occasion. And this is an animal seen with 2 tags and being alive, an animal being seen with 1 tag and being alive, and an animal that has not been seen. And here, again, as a reminder, only the first 2 states are observable with probability p and not being seen with probability 1 minus p. In this case, I assume that the recapture probability is the same between both tag states. This could be adjusted with tag number-specific recapture probabilities. And then the last 2 states, so 0 tags and alive and dead, are both seen, not seen. So the not seen column gets the probability set to 1. So I hope that was clear to everyone. So this was the basic or the rationale between of developing a tag loss model in a mark recapture context, and I now provide a technical demonstration of how this can be written up in JAX, but you can use any other language if you want, obviously. I just want to highlight that the coding I'm presenting here is based on a book by Carey and Sharp, which is a very good introduction into Bayesian modeling and state-space modeling. And this is what I'm basing this on here. So first, I define 4 components. First, simply our prior distributions. Then the metrics for the state process, so for our survival and tag loss. A metrics for the observation process, for our observation probability P, and then our likelihood, so basically coding up our categorical distributions that I described before. For price, this is pretty simple. We need price for all 3 probabilities, so for survival phi, for recapture P, and tag loss Q. In this case, I assume weakly informative priors, so using uniform priors between 0 and 1. And then just a reminder, this is what we're trying to code up, plus our dead state, which is not shown here. And this is, again, our metrics for the state process. And in JAX, we simply can code this up by defining, by assigning the different probability statements, by indexing a matrix like across rows and columns. So here's just an example of the first row in this matrix, what I called omega very early in the presentation, and how to code this up in JAX. And then we do this for every single row. And we do the same for the observation process. And last, we need to code up our likelihood. So that means our draw from the categorical distribution for the state process, and the same for the observation process. Again, a reminder, we assume that the first observation, so the first occasion is fixed basically to the first observation, or in this case 1, so the animal being alive and wearing 2 tags. And then for every subsequent state, we draw our value from the categorical distribution. In this case, it's parameterized again through matrix sigma, or coded up as PS, and this takes simply the row that is determined by the current state of individual I. So if the individual is in its first state, this will also be the first row of this matrix here, and then all the different probability statements are drawn from that. And finally, we do the same for the observation process, and that is basically the whole structure of a mark recapture model that accounts for tag loss. So I'd like to wrap up this presentation with a very quick and dirty simulation that I coded up to show that this model works, and also to, again, demonstrate the implications of tag loss. So what I've done here, I simulated a data set where for a single cohort of 500 double-tagged individuals that I followed over the period of 15 years. So I only really modeled 1 cohort, no further marking of animal happened, just for simplicity. And I've done this for 4 different scenarios. In all 4 scenarios, I assumed the same survival rate, set to 0.7. And in the first scenario, I assumed some moderate recapture probability of 0.6 and no tag loss, just as a reference. In the second scenario, I used a higher recapture probability of 0.8 and assumed that some tag loss occurs. So in this case, 10% of individuals are losing their tags, so Q equals to 0.1. Third scenario was, again, a high recapture probability of 0.8 and some moderate tag loss of 0.5, so 50% of individuals are losing their tags. And finally, a scenario with some moderate recapture probability of 0.6 and low to moderate tag loss, which I defined as 30% of animals losing their tags, so Q equals 0.3. And here are the results. So I fitted 2 models. First, I fitted a CJS model that does not account for tag loss, just to look at the potential bias. And then I also fitted the model that I just introduced in this presentation here, so a CJS model with tag loss. First, the data set or the simulation without tag loss. And obviously, I only was able to fit the CJS model that does not account for tag loss here because there is none. And what we see here are the median estimates in the 95% credible interval. And the model is estimating both parameters, so survival and recapture, pretty accurately. So the median estimate here for survival was 0.96 compared to the actual survival of 0.7, and the 95% credible interval range between 0.67 and 0.71. And again, the same accuracy for the recapture probability. The second model was fitted to a data set with a very low or low tag loss of 0.1, and here the model without tag loss still provides a very accurate and also precise estimate, actually. So the median estimate here was pretty much bang on. And on the right-hand side here, you see the estimates for the CJS model that has tag loss integrated. And here the survival estimate is actually slightly high, 0.72 compared to 0.7, and the credible interval just includes the actual 0.7. Here we need to bear in mind that with a tag loss probability of 0.1, 90% of tags are still left after the first year, and then 90% of these tags are left in the subsequent years. So most individuals actually are still wearing at least one tag. That means the tag loss model is probably struggling to estimate simultaneous tag loss. But it also means that a model with such low tag loss, a normal CJS model that does not include tag loss, is probably working pretty well still. The third scenario was a model where animals, about 50% of individuals lose their tags, and now we see the implications there, where we see that where if we don't account for tag loss, survival is seriously underestimated. So instead of the actual 0.7, the model would estimate a survival probability of 0.46, and the credible interval would be between 0.43 and 0.48. But if we account for tag loss, then we get a fairly accurate estimate. The median estimate here would be 0.76, and the credible interval between 0.62 and 0.73. Again, the actual estimate would be 0.7. And we also see that the tag loss rate is reasonably accurately estimated. Finally, a model with slightly lower recapture and also lower tag loss rate. And again, the same result, basically, a seriously underestimated survival rate in case of a CJS model that does not account for tag loss. But if we include tag loss, then we are able to estimate the actual survival rate. So I hope this was helpful to some of you. And of course, this is a very simplified version of a tag loss model that I explained here. And there are various other factors that I haven't accounted for and would make this a much more complex model. There are obviously issues with non-independent tag loss. That means if one tag sheds off one flipper, for example, that might also increase the chance of the second tag being lost. This would be very difficult to estimate with such a model or with such a study because there are no alternative means to identify individuals. So we would require some more permanent markings, such as brandings or other means. And another more recently discovered or at least described issue is also the recycling of individuals that have lost all their tags. So in this example here or study, it's not an issue. Here in my example, individuals are assumed to be only tagged early in life and not tagged as adults. That means, but if an animal is retagged also as an adult, what could possibly happen is that you tag the animal early on, it's losing both of its tags, and then the animal is re-tagged later in life, assuming this is a new individual in the pool of tagged individuals. And so this is referred to as recycling, and that has been shown to result in overestimates of population size, for example. Also not accounted for here is age-dependent tag loss, which could be simply accounted for by adding some age structure to the multi-state model. And obviously tag loss can also change with time, for example, within a year, which would require some adjustments here. And this is just like some points. There are various other things that need to be accounted for when we deal with tag loss. So yeah, thanks for listening. And if you have any questions, then I try to do my best to give a helpful reply. And yeah, looking forward to this.
Thanks very much, Stefan. That was a very informative talk and webinar discussing the ideas behind tag loss. Because he's getting some applause from different people. If anyone does have any questions, then please post them into the Q&A section of the chat. So you should find a little icon up the top of your Teams screen. While we're waiting, Stefan, I've got a couple of questions here for you. So you describe a situation where we have double tags. That's been your focus, although a lot of mark-recapture studies will only have a single tag. Just wanting your thoughts on, firstly, you demonstrated with the simulation study that we get a bias if we don't account for tag loss with two tags. Is that going to be sort of worse if we only have a single tag situation? And then sort of a follow-up question is, what can we do about it if we do only have a single tag and we suspect there's tag loss?
Well, if we have only a single tagged individuals, I mean, with the two tagged individuals, if tag loss is low, we saw that not accounting for tag loss is not having such a serious effect on our model estimates, because there's still always enough individuals left with a single tag. But if you have a single tag from the beginning, then obviously we probably, if tag loss is big enough, we losing a lot of animals from the pool of marked individuals. So we get we probably get a biased estimate even at a very low tag loss rate. And then for your second question, well, one way to deal with that issue would be to at least permanently mark some fraction of the individuals to estimate the tag loss rate, and that could be used as a factor in a model that is fitted to individuals that are single tagged only.
All right, thanks, Stefan.
Yeah.
Would it be possible if we had an estimate of tag loss from another data source to incorporate that into an analysis?
Yes, it's basically what I said, right? It would be independent pool of individuals. Yeah, but it should be from the same population, basically, I guess, because the factors that can lead to tag loss might be different from one population to another.
Yep, that sounds good.
Yeah.
Question here from Josh. Can you speak broadly about the issue of non-identifiability of parameters? For example, if you were to relax the assumption of closure to entries in the Jolly-Sieber model, what modification would you need to make to disentangle individuals which are new entries as opposed to lost both tag individuals?
I try to, not sure whether I fully understand the question. I guess this is almost similar to the issue of recycled individuals. I assume if you have, so maybe Dell, you can also clarify. So we're dealing with individuals that have entered the pool of available individuals, I assume, right?
So Josh's question again, what modification would you need to make to disentangle individuals which are new entries as opposed to lost both tag individuals. So essentially, if we've got new recruits coming to the population, as opposed to lost both. So good question, Josh. You got me thinking as well.
Yeah.
I mean, in that situation, I think perhaps it's not necessarily a tag loss question, or it's a situation where we actually probably need some additional information because there would be perhaps parameters that aren't identifiable. So things like perhaps robust design, rather than just a simple single recapture only with each sort of sampling occasion. Stefan, do you have any further thoughts?
Yeah, I guess under non-identifiability, I would rather understand a parameter that is not estimable, such as if we try to estimate non-independent tag loss but have no further information. I think we would be able to estimate something, but with a strong bias, as in my population size example. Yeah, I think we would require further information to see how many individuals would enter the pool, like new recruits, basically.
Yeah, I think it's probably the case that more information from some source.
Yeah.
Good question, Josh. You got us both thinking.
Yeah.
A question from Adriana. Could you incorporate in the model if one of the tags is not individually identifiable, for example, spine clipping of crabs, or a tag that has worn away and number is not readable? So you would know it was a tagged animal, but not which animal. Can that information be incorporated to model into the model to inform tag loss probability? So I think essentially if you have a batch mark as one of your tags, or it's a case perhaps you can see the hole in the flipper where the tag was, but you can't see it anymore, so you know it used to have a tag. Can that information be incorporated into the analyses?
My initial response is yes. You basically just have to expand the model by different states, and you would also obviously assume different resite probabilities for these states. So, for example, if it's just a hole that is left, then you would know the animal is alive and you've seen it, but you haven't you've probably seen it with a less of a chance than an animal that was still wearing a tag at the time. These are just a few thoughts here for things to account for.
Yeah, and another very good question.
Yeah.
One from Abby Bratt. If you don't manage to see both sides of the animal, so you don't know if it has one tag or two, could you deal with this in the model?
Well, the assumption in this example was that you obviously have to observe both flippers. Again, this would be a model with different multi-states, basically, where you have states such as the animal being seen with both flippers and X number of text retaining, or an individual just observed with one flipper, but it could have had either one or two text retaining. I guess we might just run into some identifiability issues here, because you also need a lot of different recapture probabilities for each of the different states.
It's kind of similar to Adriana's sort of situation. Yeah. A question from RK. They're an undergraduate student interested in studying whales and found the modeling very interesting. Has this kind of tag loss been tested and verified by actually putting two tags on the animals?
Yes, I mean, for the sea lion example is an example where actually two tags were applied, and in fact, in that original study, individuals have also received some permanent markings, such as brandings, and Daryl, for example, worked on that in the past, and so a similar model has been applied, but just also accounting for basically just also in the animals that have received permanent markings, so you can verify it. Yeah.
Thanks, Stefan. We've got two more questions here that we'll take, and then we'll we'll call the webinar to an end. So one from Sania. If we recapture an individual with a single tag, will adding a tag, making it 2 tags again, improve the estimation?
Yeah, that's basically if the estimation, I assume the estimation in a normal CGS model, not including tag loss, it would if tag loss is small, right? Because we simply increase the chance that there are animals left with at least 1 tag, and therefore we can observe them. Yeah.
Cool. All right. Final question. This one comes from Kaya. Are there any non-Bayesian approaches where you can incorporate tag loss if you have an estimate of tag loss rate?
Yeah, basically, yes, you can also implement a multi-state model, for example, using just maximum likelihood estimation and account for that. The Bayesian modeling is just a preference and makes it maybe a little easier to code it up and also to include uncertainty of the tag loss estimate.
Yep. No, awesome. Thank you very much, Stefan. So there you have, we'll call it to a close. Thanks everybody for attending today. I hope you found the webinar informative. And so we'll put a recording out for those that want to review it again, and also put it up on our YouTube channel. And certainly, if you want to find out more about Proteus, you can come along to our website and just learn a bit more about what we do. And keep an eye out for webinars that we'll be running in the future in approximately sort of 3 months' time. Thanks, everybody, and enjoy the rest of your day.